Here we delve into the atom, where we describe and define certain concepts of atoms based on its combination of subatomic particles, electrons, protons, and neutrons. Write down this equation. 1 AMU is 1.66 times 10 to the negative 24 grams. An atomic mass unit just happens to be the mass of a proton and of a neutron. For an electron, on the other hand, it is so tiny that we just ignore it. Now, the number of protons, and thus the atomic number for any element, is always the same because it defines that element. Carbon has an atomic number of 6 because there's 6 protons in carbon. If carbon had 7 protons, it would no longer be carbon, it would be nitrogen. Charge, on the other hand, is the number of protons minus the number of electrons. It works out this way because their individual charges are equal and opposite, +1 and -1 respectively. An ion is an atom or molecule with a charge, and this occurs when the substance has an uneven number of protons and electrons because P minus E does not equal 0. Likewise, if our ion is positively charged, it's a cation. If it's negatively charged, it's an anion. When we have a molecule with a charge, it's a polyatomic ion, and if it were positive, it would be a polyatomic cation and polyatomic anion respectively. Isotopes are a little different. They exist for particular elements, and different isotopes for a particular element are different solely on the basis of neutron counts. Carbon-12 and carbon-13, for example, which we'll see on future slides, each have 6 protons, but one has 6 neutrons, the other one has 7 neutrons. Isotopes vary in mass in the following way. A property of an isotope is the mass number, which is simply the mass of all the protons, electrons, and neutrons which compose it. Since, as I said, the electron is so negligible in its mass, we just neglect it. Thus, the mass number of an isotope is the number of protons plus the number of neutrons. And this works out evenly because each has an individual mass of 1 AMU. So if we had 10 protons and 5 neutrons, the total mass would be 15 AMU, or the mass number would be 15. The whole thing I want you to pay attention to with this is the fact that Z, which is the atomic number, is the same thing as P, the number of protons, and that becomes relevant in the mass number equation. Here's isotope notation. We've got our chemical symbol, which defines the element. We've got our mass number, which is the sum of protons and neutrons, and we've got our atomic number, or the number of protons. Another thing that we can do is highlight the net charge, or the charge of the isotope if it has one. If it doesn't have one, there is no point in saying 0. We can just imply that it doesn't have a charge if we don't write anything. Here's an example of a carbon isotope where it's got a mass number of 12, 6 protons because it's the atomic number, and it's got a charge of -2, meaning that it's got 2 more electrons than protons. Another way of writing that is carbon-12 with a 2 minus, and in both cases, we know we can infer the total number of all 3 subatomic particles. Now, if we kept everything the same, but it was carbon-13, the only thing that would be different is the number of neutrons. Now, it's just a coincidence that they both have the same charge in this instance. You could have carbon-12 with a +1 charge, or you could have a carbon-13 with a neutral charge. What does this all have to do with the number on the periodic table? It's between 12 and 13, and we just went over carbon-12 and carbon-13, which have a mass of 12 AMUs and 13 AMUs respectively, and they all have to be integer amounts, 1, 2, 3, 4, 5, etc. How do we have this number that has a decimal? Now, this number has many different interpretations, but for the sake of this video, 12.011 is the number of AMUs, or the mass of the typical carbon atom. In other words, it's seen as a composite average of all existing isotopes of carbon scaled to their relative abundances. So if we know that we have 12 AMU isotope and a 13 AMU isotope, the average is not 12 plus 13 divided by 2, it's that, but it's scaled to their relative abundances, 0.99 and 0.01 respectively. You add it up, and what we're left with is a composite average of all existing isotopes, known as an average atomic mass. Here are some typical questions that you might receive for this topic, and if you click right here or right here, here are the solutions to those problems.